Okay, so in this particular problem, we're going to be wanting to try to figure out what is the maximum force that we can push on this crate without the crate moving. Okay, without the crate moving. So let's go ahead and get some forces on here. So we're going to have some friction back this way. There's a certain coefficient of friction there, and so it's going to be important to end up getting the normal force at some point. But anyway, so there's our friction there, and we're going to have some weight here, and then we're going to have some kind of normal force here. Okay, and that's all we got on this one. Okay, so let's go ahead and get to our equilibrium equations. So, oh, it's too big, too big, too big, too big. I'm going to do it right over here. Okay, so here, what we're going to have, if we look horizontally, we have P minus the friction is 0, and that tells us to be in equilibrium, it's going to have to be equal to the frictional force. Okay, now this is static friction, and so that means really we're going to have one of these conditions here. And so P is going to have to be less than or equal to mu times the normal force. So once we get that normal force, then we can turn around and plug in and get some idea about our friction, okay? So let me scoot, I guess I'll just do it down here. This will be fine. So looking at what's happening vertically, it's as easy as it gets, right? Okay, and the weight, this thing, they give it to us in English units. It's 250 pounds, just like that. Okay, so let's take that information and put it in for our normal force. So that's going to tell us then that P has to be less than or equal to 0.4 times 250. Okay, and that's equal to 100. So P must be less than or equal to 100. Okay, now so far what that tells us is the maximum force that the friction can withstand. Okay, so the friction can handle up to 100. So is that it? Are we done here? Well, you know there's more video coming, so clearly we're not done here. All right, so look at all these dimensions. 4.5 feet, 3.5 feet, 2.5 feet, 1.5, 1.5. All right. We haven't seen dimensions like that put into a problem unless we're dealing with moments. Okay, so can this thing fall down or not? Okay, so we've got this thing sitting here. We're going to push on it here. We've said there's a limit to keep it from sliding, which goes up to 100. But what about tipping over? We haven't had to worry about tipping over before, but now we're going to worry about tipping over. Okay. So what we'll do is let me zoom up a little bit here. We're going to put a pivot here, and let's call this X. Okay. And we're going to act like the normal force is concentrated in some particular location. Now, the reality actually is that our normal force is going to have some kind of distribution. Okay, and so if we knew that distribution, then we could find out where the center, or where that force is concentrated. Okay. What we're doing is kind of like backwards. Instead of finding where a distributed load is concentrated, we're going to find the point of concentration and not know what the distribution actually is. Okay. So we do that over here by summing our moments. Okay. So our moment's equal to 0. And so P, the force P is up there at 4.5 feet, and it's negative. And then I've got weight, and it's out there a distance of 1.5, also negative. And then I've got my normal force, which is my only positive moment, at a distance of x. Okay? Now, what we'll do is we're going to plug in the maximum, P equal to 100, and see what happens. Okay? So if we go and do that, minus 4.5 times 100, that's a 5 there. Okay. Minus 1.5 by 250 plus x times 250 equals 0. And when we solve that, what we're going to get is 3.3. Okay, awesome. 3.3. So now we know where that's located. Okay, so let's get an idea about that. Okay, so this is 1.5. That's, 3.3 is actually over here. So that's not cool. All right, what that means is if we pushed with 100, it might not slide, but it's going to tip over. Okay, in order to keep it from tipping, we would need some kind of a brace or something there propping that thing up so that we could have contact beyond that 3.3 distance. Okay, so, all right, let me get rid of some of that stuff. So what are we going to do? Well, we come back to this relationship, and what we'll do is we'll solve for P and let x be 3. Okay, now when we do that, that's going to put the normal force as far over as it can possibly go. All right, so let me do that stuff up here. So I'm going to have minus 4.5 P minus 1.5 W, which is 250, plus 3 for x, 250 for my n, and all that is equal to 0. Okay, so I've just used that equation right there. And then I can solve for P, and once you do all that, what you get is 83 1/3. Okay, 83.3333333. All right, and that also matches, that matches our criteria in terms of the maximum value. Okay, we said it has to be less than 100, and 83 1/3 is certainly less than 100. So that means that 83 1/3 is no problem for the friction when it comes to withstanding the impending motion. Okay, so let me zoom out just a little bit here. There we go. And you can kind of see how we set it up. Okay, and so we're going to have other kinds of conditions. We've seen that a couple times already, but get ready for this. So sometimes your friction itself is going to present a limitation that you got to watch out for. So you may have to find out, well, wait, is this thing slipping or not? Okay, what are my constraints? What are my limitations there? And then what are my constraints rotationally? Can this thing tip or not? All right. And so when we've got one of these situations where we said maximum force, okay, it could be a trap. Be careful. Okay. Know that you got to check for slipping and you got to check for tipping both. Tipping and slipping. Easy to remember.